There is a strange and invisible dance taking place all around us, one that governs the very fabric of our reality. It's a dance of particles, waves, probabilities, and mysteries that challenge the deepest assumptions we hold about existence. At the heart of this dance is quantum mechanics, a branch of physics that doesn't just push the boundaries of our understanding but shatters them. As we dive into the realm of space mysteries, quantum mechanics unveils a universe that behaves in ways so bizarre, so unintuitive, that it seems ripped from the pages of science fiction. This is a universe where particles exist in multiple places at once, where objects separated by vast distances are mysteriously connected, and where the very act of observation changes reality itself. But before we continue, if you like this type of videos, please subscribe to the channel and comment. Imagine standing at the edge of a cliff, peering into the vast cosmos. The stars shimmer in the distance, planets orbit silently, and black holes consume everything that crosses their event horizon. It's a beautiful, orderly scene, one that we've grown familiar with, thanks to classical physics. But now, picture yourself looking deeper, beyond the stars, into the very quantum fabric of the universe. Here, the predictable rules of space and time break down. Reality becomes less like a solid object and more like a web of probabilities, with every possible outcome coexisting until one is chosen. It's this world, the quantum world, that holds the keys to some of the deepest space mysteries ever pondered. Quantum mechanics begins with an unsettling premise, that on the smallest scales of reality, particles behave in ways that defy common sense. These particles, the fundamental building blocks of the universe, don't move in neat, straight lines like we might expect. Instead, they seem to flicker in and out of existence, teleport from one place to another, or even exist in multiple states simultaneously. This phenomenon is encapsulated in the principle of superposition. In simple terms, superposition suggests that particles can be in two or more states at once. A famous thought experiment, Schrödinger's cat, illustrates this paradox. If you placed a cat in a box with a quantum particle that had a 50-50 chance of decaying and releasing a deadly gas, the cat would, in some strange sense, be both alive and dead until you opened the box. It's only the act of observing the cat, peering into the box, that forces the universe to choose a reality. This experiment highlights one of the most mind-bending aspects of quantum mechanics, the idea that observation itself changes reality. This is not just a quirky thought experiment. In the quantum realm, experiments have shown time and again that particles behave differently when they are observed. But what does this mean for the nature of reality itself? If the universe only decides on a specific outcome when observed, then does reality even exist without an observer? Quantum mechanics seems to suggest that the universe is, at its core, probabilistic rather than deterministic. In other words, rather than unfolding according to a set plan, reality exists in a superposition of possibilities until we, as observers, play our part. This concept leads to a profound philosophical question. Is consciousness fundamental to the nature of reality? Could the universe itself, in some way, be shaped by the minds that observe it? While quantum mechanics doesn't provide clear answers to these questions, it certainly raises them, and the implications stretch far beyond the quantum scale. One of the most puzzling aspects of quantum mechanics is the phenomenon known as quantum entanglement. When two particles become entangled, they share a connection that defies classical understanding. No matter how far apart these particles are, changes to one instantaneously affect the other. Albert Einstein famously called this spooky action at a distance, as it seemed to violate the universal speed limit set by the speed of light. Imagine two particles, entangled and separated by the vast distance between Earth and the nearest star. If you were to measure the state of one particle here on Earth, you would instantly know the state of the other, even if it were light years away. This defies our intuitive understanding of space and time, suggesting that at the quantum level, reality is more interconnected than we could have ever imagined. In recent years, scientists have been able to experimentally verify quantum entanglement, proving that it is not just a theoretical curiosity but a real phenomenon. But the deeper question remains, what does entanglement tell us about the fabric of the universe? Some theorists suggest that quantum entanglement hints at the existence of a hidden layer of reality, one where space and time as we know them don't exist. Instead, everything might be connected in ways that our current understanding cannot explain. This has led to fascinating new ideas in the field of quantum gravity and the nature of spacetime itself. Could the seemingly empty space between stars and galaxies be filled with a hidden web of quantum connections? And if so, what role do these connections play in the grand structure of the cosmos? Quantum mechanics also raises profound questions about the origins of the universe itself. The Big Bang, the event that gave birth to our universe, remains one of the greatest mysteries in modern science. According to the prevailing theory, the universe began as a singularity, a point of infinite density and temperature, where the laws of physics as we know them break down. But what role did quantum mechanics play in this primordial event? Some scientists believe that the quantum realm holds the key to understanding the birth of the cosmos. In the moments before the Big Bang, the universe might have existed in a quantum state, where all possible outcomes existed simultaneously. The act of observation, in a cosmic sense, might have been the trigger that collapsed this superposition into the universe we inhabit today. This idea is closely related to the concept of quantum fluctuations. In the vacuum of space, particles are constantly popping in and out of existence due to quantum fluctuations. These fluctuations are usually so small that they go unnoticed, but on the scale of the early universe, they might have played a pivotal role in shaping the cosmos. Some theories even suggest that the universe itself could have emerged from a quantum fluctuation, an ephemeral blip in the quantum fabric that gave rise to everything we see around us. If true, this would mean that the universe, in a sense, emerged from nothing. Quantum mechanics would then be the underlying mechanism that brought the universe into being, challenging our very understanding of creation and existence. Another profound mystery lies in the relationship between quantum mechanics and black holes. Black holes are regions of spacetime where gravity is so intense that not even light can escape. According to classical physics, anything that falls into a black hole is lost forever. But quantum mechanics tells a different story. Stephen Hawking famously proposed that black holes might not be completely black after all. Due to quantum effects near the event horizon, black holes could emit a faint glow, now known as Hawking radiation. Over time, this radiation could cause the black hole to shrink and eventually evaporate entirely. This presents a paradox. If black holes can disappear, what happens to the information they once contained? According to the laws of quantum mechanics, information cannot be destroyed. But if black holes can evaporate, does this mean that information can be lost? This information paradox remains one of the biggest unsolved problems in modern physics, and its solution could revolutionize our understanding of the universe. As we venture further into the unknown, we encounter the many worlds interpretation of quantum mechanics. This theory suggests that every possible outcome of a quantum event actually occurs, but in separate, parallel universes. Imagine flipping a coin. In one universe, the coin lands heads, and in another, it lands tails. These universes coexist, branching off from each other with every quantum event. According to the many worlds interpretation, there is a virtually infinite number of parallel universes, each with its own version of reality. In some universes, you might have taken a different path in life, or the stars might have formed in different patterns. While this theory is controversial, it offers an intriguing solution to some of the puzzles of quantum mechanics, particularly the problem of superposition. If every possible outcome occurs in some universe, then there's no need for the universe to choose a single reality. The many worlds interpretation also has profound implications for our understanding of free will and the nature of time. If every decision we make leads to a branching of realities, does that mean that all possible versions of ourselves exist somewhere in the multiverse? And if time itself branches off with every quantum event, is the flow of time as we experience it merely an illusion? These are questions that quantum mechanics forces us to confront, and while we may not yet have the answers, the very act of asking them challenges our most fundamental beliefs about the nature of existence. Another quantum mystery that has fascinated scientists is the nature of the quantum vacuum. Contrary to what we might expect, the vacuum of space is not empty. Instead, it is teeming with virtual particles that blink in and out of existence, a phenomenon known as vacuum fluctuations. These virtual particles play a crucial role in the behavior of the universe, contributing to forces like the Casimir effect and potentially influencing the expansion of the cosmos. Some theories even suggest that the energy of the quantum vacuum could be harnessed to create exotic forms of matter or even warp spacetime itself, opening up the possibility of faster-than-light travel and other science fiction-like concepts. As we delve deeper into the mysteries of quantum mechanics and space, we must confront the limits of our current understanding. While quantum mechanics has given us remarkable insights into the workings of the universe, it is far from a complete theory. The biggest challenge lies in unifying quantum mechanics with general relativity, the theory that governs the behavior of gravity and large-scale structures like stars and galaxies. These two pillars of modern physics work remarkably well in their respective domains, but when combined, they seem to be fundamentally incompatible. This has led to the search for a theory of quantum gravity, a framework that would reconcile these two aspects of reality and provide a deeper understanding of how the universe works on both the smallest and largest scales. The search for a theory of quantum gravity is one of the most significant ongoing quests in theoretical physics, and it might hold the key to solving some of the deepest space mysteries. One promising candidate for a theory of quantum gravity is string theory. String theory proposes that the fundamental building blocks of the universe are not point-like particles, as described by quantum mechanics, but tiny, vibrating strings of energy. These strings can vibrate in different ways, giving rise to the various particles we observe, like electrons, quarks, and photons. But the most remarkable aspect of string theory is its ability to unify all the forces of nature, including gravity, in a single framework. According to string theory, gravity is just one of many manifestations of these vibrating strings, and the familiar particles and forces we experience in our everyday lives are all connected by a deeper, underlying structure. If true, string theory could finally provide the missing link between quantum mechanics and general relativity. However, string theory comes with its own set of mind-bending implications. For one, it requires the existence of extra dimensions beyond the familiar three of space and one of time. In some versions of string theory, the universe has as many as 11 dimensions, most of which are hidden from our perception. These extra dimensions could be compactified, meaning they are curled up so tightly that they are imperceptible at our scale. But on the quantum level, they might play a crucial role in the behavior of particles and forces. This raises the intriguing possibility that there are hidden aspects of the universe, dimensions of reality, that we are completely unaware of, yet which profoundly shape the structure of the cosmos. String theory also introduces the concept of brains, short for membranes. In this framework, our universe might be a three-dimensional brain floating in a higher-dimensional space. Other brains, representing other universes, could exist alongside ours, separated by tiny distances in these extra dimensions. This gives rise to the idea of a multiverse, a vast ensemble of parallel universes, each with its own physical laws and constants. Some of these universes could be radically different from our own, with different forms of matter, forces, and even different dimensions. If the multiverse theory is correct, then our universe might be just one of many, a single bubble in an infinite cosmic foam. This idea is both exhilarating and humbling, as it challenges our perception of the universe as a unique and isolated entity. The multiverse theory also ties into the question of why our universe appears to be so finely tuned for life. The physical constants of the universe, such as the strength of gravity and the charge of the electron, seem to be set at just the right values to allow stars to form, planets to exist, and life to emerge. If these constants were even slightly different, the universe might be a barren, lifeless place. This has led some scientists to propose the anthropic principle, which suggests that the universe appears fine-tuned because we are here to observe it. In a multiverse, there could be countless universes with different physical laws, most of which are inhospitable to life. We just happen to live in one of the few universes where the conditions are right for our existence. While this is a compelling idea, it raises more questions than it answers. Is the multiverse real, or is it just a convenient way to explain the apparent fine-tuning of our universe? Another space mystery that intersects with quantum mechanics is the nature of dark matter and dark energy. Together, these mysterious substances make up about 95% of the total mass and energy in the universe, yet they remain almost entirely invisible to us. Dark matter is thought to be responsible for the gravitational effects that hold galaxies together, while dark energy is driving the accelerating expansion of the universe. Despite decades of research, we still don't know what dark matter and dark energy are made of or how they fit into the framework of quantum mechanics and general relativity. One possibility is that dark matter consists of particles that interact only weakly with ordinary matter, making them difficult to detect. These particles might belong to a new class of particles predicted by extensions of the standard model of particle physics, such as supersymmetry. Supersymmetry suggests that every known particle has a heavier partner, or superpartner, that could explain the properties of dark matter. However, no such particles have been discovered yet, leaving the nature of dark matter an open question. Dark energy, on the other hand, is even more mysterious. It seems to be a form of energy inherent to the vacuum of space, pushing galaxies apart and causing the universe to expand at an ever-increasing rate. Some theories propose that dark energy is related to the quantum vacuum, the seething sea of virtual particles that constantly pop in and out of existence. Others suggest that dark energy is a manifestation of a new force of nature, one that we have yet to fully understand. Whatever its true nature, dark energy is one of the most profound space mysteries, with implications for the ultimate fate of the universe. As we contemplate these quantum mysteries, we must also grapple with the philosophical implications of quantum mechanics and the nature of reality. One of the most startling conclusions of quantum mechanics is that reality is not fixed and objective but is shaped by the act of observation. This has led some physicists and philosophers to question the very nature of existence. Is the universe fundamentally indeterminate, with all possibilities existing until they are observed? If so, does this mean that reality is created by consciousness? Could the universe itself be a kind of vast, interconnected web of information, where the physical world we experience is just one layer of a deeper, more fundamental reality? These questions are not just abstract philosophical musings. They have real implications for our understanding of space, time, and the cosmos. If quantum mechanics suggests that reality is shaped by observation, then the nature of time itself might be more fluid than we imagine. Time, as we experience it, appears to flow in one direction, from past to present to future. But at the quantum level, time might not be a fixed arrow. Some interpretations of quantum mechanics suggest that the future can influence the past, or that time is a loop, with events in the present affecting both the past and the future. This challenges our conventional understanding of causality and opens up new possibilities for how the universe operates. Quantum mechanics also raises the question of whether the universe is deterministic or probabilistic. In classical physics, the universe is governed by deterministic laws, where every event has a cause, and the future is predictable if we know the initial conditions. But in the quantum world, events are governed by probabilities, not certainties. This means that the universe is fundamentally unpredictable at the smallest scales, with no way to know for sure what will happen next. This indeterminacy has profound implications for free will and the nature of existence. If the universe is governed by probabilities, then does this mean that we live in a world of chance, where the future is not set in stone but is constantly being shaped by random events? As we venture further into the mysteries of quantum mechanics and space, we must also confront the limitations of our current tools and methods of observation. Much of what we know about the universe comes from indirect measurements and mathematical models, rather than direct observation. The quantum world is so small and so strange that it often defies our ability to visualize or comprehend it. We rely on abstract mathematical equations and complex experiments to infer the behavior of particles and forces at the quantum level. But there is always the possibility that our models are incomplete, that we are missing key pieces of the puzzle that could revolutionize our understanding of the universe. In recent years, advances in technology have allowed us to probe deeper into the quantum realm than ever before. Experiments with particle accelerators, such as the Large Hadron Collider, have provided new insights into the fundamental forces and particles that govern the universe. Quantum computing, a field that harnesses the principles of quantum mechanics to perform calculations, has the potential to revolutionize not just technology but our understanding of reality itself. By simulating quantum systems and solving problems that are impossible for classical computers, quantum computing could unlock new discoveries about the nature of the universe. One of the most exciting developments in quantum research is the exploration of quantum gravity. If we can find a way to unify quantum mechanics with general relativity, we might be able to solve some of the greatest space mysteries, such as the nature of black holes, the Big Bang, and the ultimate fate of the universe. The quest for quantum gravity has led to several intriguing theories, including loop quantum gravity and causal set theory, which offer new ways of thinking about the fabric of spacetime. While these theories are still in their early stages, they represent a bold attempt to bridge the gap between the quantum and cosmic scales. It becomes clear that we are only scratching the surface of the universe's deepest secrets. Quantum mechanics has opened a window into a reality that is far stranger and more mysterious than we ever imagined. It has forced us to rethink our most basic assumptions about the nature of reality, time, space, and existence itself. And yet, for all the progress we have made, many questions remain unanswered. What is the true nature of quantum entanglement? How do quantum particles interact with the fabric of spacetime? What role does consciousness play in shaping reality? And how do these quantum mysteries fit into the larger structure of the cosmos? The answers to these questions may lie in the distant future, or they may be just around the corner, waiting to be unlocked by the next breakthrough in science. What is clear, however, is that the universe is a far more complex and enigmatic place than we ever thought possible. From the smallest quantum particles to the vast stretches of space, we are surrounded by mysteries that challenge our understanding of reality itself. And as we continue to explore the frontiers of quantum mechanics and space, we may uncover truths that not only reshape our scientific understanding but also transform how we view our place in the cosmos. One of the key insights that quantum mechanics offers us is the interconnectedness of all things. In classical physics, objects and particles are seen as distinct, isolated entities, interacting with each other through forces like gravity or electromagnetism. But in the quantum world, particles are entangled, their states linked together no matter how far apart they are. This phenomenon, known as quantum entanglement, is one of the most puzzling and counterintuitive aspects of quantum mechanics. When two particles are entangled, a change in the state of one particle will instantly affect the other, even if they are separated by vast distances. This spooky action at a distance, as Einstein famously called it, seems to defy the laws of classical physics, particularly the principle that nothing can travel faster than the speed of light. Entanglement challenges our very notion of space and distance. It suggests that, at a fundamental level, the universe is not made up of separate, independent objects, but rather of interconnected systems that influence each other instantaneously. This idea is not only strange but deeply profound, as it implies that the separation we experience between objects in space might be an illusion created by our limited perception. In reality, the universe could be a single, unified whole, with all parts intricately connected through invisible quantum links. Some physicists have even speculated that entanglement could be the underlying structure of spacetime itself, with the fabric of the universe woven together by these quantum connections. Entanglement has been experimentally verified in countless studies, yet its implications remain a mystery. How can two particles communicate instantaneously across vast distances? What is the medium through which this information is transferred? And if entanglement truly connects all things, what does that mean for the nature of space, time, and causality? Some researchers believe that answering these questions could lead to breakthroughs in fields ranging from quantum computing to cosmology. Another space mystery that is deeply intertwined with quantum mechanics is the behavior of black holes. Black holes are regions of spacetime where gravity is so strong that not even light can escape. According to general relativity, black holes form when massive stars collapse under their own gravity, creating a singularity, a point of infinite density and zero volume where the laws of physics, as we know them, break down. At the singularity, the equations of general relativity no longer apply, and quantum effects become dominant. This makes black holes one of the key battlegrounds for understanding how quantum mechanics and gravity interact. One of the most perplexing questions about black holes is what happens to information that falls into them. In classical physics, information about a physical system, such as the position and velocity of particles, is always preserved. But black holes seem to violate this principle, as anything that crosses the event horizon, the boundary beyond which nothing can escape, appears to be lost forever. This led to the so-called black hole information paradox, which has puzzled physicists for decades. Does the information get destroyed inside the black hole, or is there a way for it to escape? Quantum mechanics suggests that information cannot be destroyed, even by a black hole. In the 1970s, Stephen Hawking showed that black holes are not entirely black. They emit radiation, now known as Hawking radiation, due to quantum effects near the event horizon. Over time, this radiation causes the black hole to lose mass and eventually evaporate. But if a black hole evaporates completely, what happens to the information that was inside it? This paradox has sparked intense debate among physicists, with some suggesting that the information is encoded in the Hawking radiation, while others propose that the information is somehow preserved on the event horizon itself. The black hole information paradox is not just a theoretical puzzle. It has profound implications for our understanding of the universe. If information can be lost in black holes, then one of the fundamental principles of quantum mechanics, the conservation of information, would be violated. This would require a radical revision of our understanding of physics. On the other hand, if information is preserved, then we may need to develop a new theory of quantum gravity to explain how it is stored and transmitted. One leading candidate for resolving this paradox is the holographic principle. The holographic principle suggests that all the information contained within a region of space can be encoded on its boundary, much like a hologram. In the case of black holes, this means that the information about everything that falls into the black hole could be stored on the event horizon, rather than being lost inside the singularity. This idea has profound implications for our understanding of the universe, as it implies that reality itself might be holographic, that everything we experience in three-dimensional space is actually a projection of information encoded on a two-dimensional surface. The holographic principle also ties into another deep mystery of quantum mechanics, the nature of spacetime itself. According to general relativity, spacetime is a smooth, continuous fabric that can be warped by mass and energy. But quantum mechanics suggests that spacetime is not smooth at all, but rather is made up of tiny, discrete units, much like how matter is composed of atoms. At the Planck scale, the smallest possible length scale, spacetime might be a chaotic, frothing sea of quantum fluctuations, constantly bubbling and shifting in ways that defy our everyday experience. This idea of quantum spacetime has led to the development of theories such as loop quantum gravity, which attempts to describe the structure of spacetime at the quantum level. In loop quantum gravity, spacetime is composed of tiny loops, or quanta, that form a network of connections. These loops are incredibly small, about 10 to the power of -35 meters in size, but they are thought to be the fundamental building blocks of the universe. If loop quantum gravity is correct, then space and time are not continuous, but discrete, much like the pixels on a computer screen. This would mean that the smooth flow of time we experience is an illusion created by the interactions of these tiny quanta. The implications of quantum spacetime are mind-boggling. If space and time are quantized, then what we perceive as the fabric of the universe is actually a vast network of interconnected loops, constantly fluctuating and interacting at the smallest scales. This challenges our classical understanding of geometry and could revolutionize our understanding of everything from black holes to the Big Bang. It also raises profound questions about the nature of time itself. Is time a fundamental property of the universe, or is it an emergent phenomenon that arises from the interactions of quantum particles? Could time be an illusion, with all events in the universe existing simultaneously, waiting to be unfolded by consciousness? These questions lead us to one of the most profound space mysteries of all, the origin of the universe itself. The prevailing theory of the universe's origin is the Big Bang, a moment when the universe suddenly expanded from an incredibly hot, dense state into the vast cosmos we see today. But what caused the Big Bang? And what came before it? Quantum mechanics offers some tantalizing clues. One possibility is that the Big Bang was not a singular event, but part of a larger, ongoing process. Some theories propose that the universe is cyclic, with periods of expansion followed by periods of contraction. In this view, the Big Bang was not the beginning of time but simply the latest in a series of cosmic cycles. Other theories suggest that the Big Bang was the result of a quantum fluctuation in a pre-existing vacuum, a kind of quantum bubble, that suddenly expanded to create the universe. This idea ties into the concept of quantum foam, the frothy sea of virtual particles that constantly pop in and out of existence at the smallest scales. Quantum fluctuations could also be responsible for the creation of multiple universes in a multiverse. If the quantum vacuum is constantly fluctuating, then it could give rise to countless pocket universes, each with its own set of physical laws and constants. This would mean that our universe is just one of many, a single bubble in an infinite sea of cosmic possibilities. The multiverse theory offers a possible solution to the fine-tuning problem, as it suggests that there are countless universes with different properties, and we just happen to live in one where the conditions are right for life. But the idea of a multiverse raises new questions. If there are other universes, can we ever detect or interact with them? Are there other versions of ourselves living in these parallel realities? And if the multiverse is real, what does that mean for our understanding of the cosmos as a whole? The mysteries of quantum mechanics and space are vast and profound, and we are only just beginning to scratch the surface. From the strange behavior of particles at the quantum level to the mind-bending implications of black holes and the multiverse, we are confronted with a universe that is far stranger and more complex than we ever imagined. As we continue to explore these mysteries, we may one day unlock the secrets of reality itself, revealing a universe that is not only beautiful and awe-inspiring but deeply interconnected in ways we are only beginning to understand. These space mysteries take us to the very edges of what we can comprehend and force us to confront fundamental questions about the nature of reality. One of the most important ideas that arises from the intersection of quantum mechanics and cosmology is the concept of superposition. In the quantum world, particles can exist in multiple states simultaneously, a principle known as superposition. This is best illustrated by Schrödinger's famous thought experiment involving a cat that is both alive and dead until it is observed. The idea of superposition is counterintuitive because in the macroscopic world we are used to objects existing in clearly defined states. But at the quantum level, particles can exist in multiple states at once, and it is only when we observe them that they collapse into a single, definite state. This leads to a deep and troubling question. What is the role of the observer in quantum mechanics? Does reality only exist when it is observed? This idea has been a subject of intense debate among physicists and philosophers alike. In the Copenhagen interpretation of quantum mechanics, the act of observation is what causes the wave function of a particle to collapse into a definite state. In this view, consciousness plays a central role in shaping reality, suggesting that the universe is not entirely objective but rather depends on the presence of observers to bring it into being. This idea is mind-boggling and challenges our traditional view of the universe as a deterministic, clockwork mechanism that exists independently of human perception. But not all physicists agree with the Copenhagen interpretation. Some suggest that the wave function never collapses, and instead, all possible outcomes of a quantum event actually occur in parallel universes. This is known as the many-worlds interpretation, and it implies that every time a quantum event occurs, the universe splits into multiple versions, each representing a different outcome. In one universe, Schrödinger's cat is alive, while in another, it is dead. According to this interpretation, the universe is constantly branching into new realities, creating an infinite number of parallel worlds. The many-worlds interpretation raises profound questions about the nature of choice, free will, and reality itself. If every possible outcome of every event occurs in a parallel universe, then there could be countless versions of ourselves living out different lives in different realities. This leads to the mind-bending possibility that every decision we make creates a new universe, one where we made a different choice. In this view, the universe is not a singular entity but a vast, ever-expanding multiverse, with infinite versions of reality existing side by side. The idea of multiple realities brings us back to one of the biggest mysteries in quantum mechanics, the nature of time. In our everyday experience, time flows in one direction, from the past to the future. But in the quantum world, the distinction between past, present, and future becomes blurred. Some interpretations of quantum mechanics suggest that time is not linear but rather exists as a block, with all events, past, present, and future, existing simultaneously. In this view, the passage of time is an illusion, a product of our limited perception. This idea is supported by experiments in quantum physics that seem to show that particles can influence each other across time, in what is known as quantum retrocausality. In these experiments, particles appear to affect the outcome of events in the past, suggesting that the flow of time might not be as straightforward as we think. If time is indeed an illusion, then our entire understanding of causality, the relationship between cause and effect, may need to be rethought. Quantum mechanics also forces us to reconsider the nature of matter itself. In classical physics, matter is made up of particles, which have definite properties like mass, charge, and position. But in quantum mechanics, particles are not solid, well-defined objects. Instead, they are described by wave functions, which represent a probability distribution of where a particle might be. In this view, particles do not have definite positions or velocities until they are observed. This leads to the strange conclusion that particles can exist in multiple places at once, or nowhere at all, until they are measured. This raises another deep question: what is matter really? If particles do not have definite properties until they are observed, then what is the true nature of the physical world? Some physicists argue that the universe is not made of matter at all, but of information. In this view, reality is fundamentally mathematical, and the physical world is a manifestation of abstract patterns of information. This idea ties into the simulation hypothesis, which suggests that the universe could be a computer simulation, with everything we experience being the result of code running on a cosmic computer. The simulation hypothesis has gained traction in recent years, with some physicists and philosophers arguing that it is not only possible but likely that we are living in a simulated reality. If the universe is a simulation, then everything we perceive as physical reality, matter, energy, space, and time, could be an illusion, created by a higher dimensional intelligence, or an advanced civilization. This would explain many of the strange phenomena we observe in quantum mechanics, such as the apparent collapse of the wave function upon observation. In a simulated reality, the universe would only render certain aspects of reality when they are being observed, much like how a video game only renders the parts of the game world that the player is looking at. The idea that we might be living in a simulation is both exhilarating and terrifying. It suggests that the universe is not as solid and objective as we think, but rather a complex system of information that can be manipulated and controlled by forces beyond our understanding. If we are living in a simulation, then what is the purpose of our existence? Are we part of an experiment, a form of entertainment, or something else entirely? And if the universe is a simulation, can we ever escape it, or are we forever trapped within this artificial reality? These questions bring us to the edge of what we can know about the nature of reality. Quantum mechanics has shown us that the universe is far stranger and more mysterious than we ever imagined. From the behavior of particles at the quantum level to the mind-bending implications of parallel universes, black holes, and the nature of time, we are confronted with a reality that defies our intuition and challenges our most fundamental assumptions about the world. The mysteries of space and quantum mechanics are not just scientific puzzles. They are profound philosophical questions that force us to confront the limits of our knowledge and the nature of existence itself. As we continue to explore these mysteries, we may one day unlock the secrets of the universe, revealing a reality that is even more wondrous and awe-inspiring than we can currently imagine. But for now, we are left with more questions than answers. The universe is a vast, enigmatic place, and quantum mechanics has shown us that we are only just beginning to understand its true nature. Whether we are living in a multiverse, a simulation, or something even more bizarre, one thing is clear: the mysteries of space and quantum mechanics are far from being solved, and the journey to understanding them will likely take us beyond the boundaries of human comprehension. Another key enigma in quantum mechanics that delves deep into the nature of reality is the phenomenon known as quantum entanglement. When two particles become entangled, their quantum states are linked in such a way that the state of one particle instantaneously affects the state of the other, no matter how far apart they are. This effect seems to violate the principles of classical physics, particularly the idea that nothing can travel faster than the speed of light, as laid out by Einstein's theory of relativity. Einstein famously referred to quantum entanglement as spooky action at a distance, because it seemed to defy the very foundations of physical law. However, experiments have consistently shown that entanglement is a real and measurable phenomenon, with particles influencing each other instantaneously over vast distances. The implications of quantum entanglement are profound, suggesting that the universe is not as separate and divided as it seems. Instead, at the quantum level, everything may be interconnected, with distant parts of the universe subtly linked in ways that we are only beginning to understand. One of the most interesting implications of quantum entanglement is its potential to reveal deeper truths about the nature of space and time. If entangled particles can communicate instantaneously across vast distances, it may suggest that space and time are not as fundamental as we think. Some physicists propose that space and time might emerge from a deeper, more fundamental layer of reality, one where the distinction between here and there, or now and then, breaks down. In this view, space and time are merely constructs that arise from a more profound underlying order that governs the universe at the quantum level. This brings us to the concept of quantum field theory, which seeks to unify quantum mechanics and relativity into a single coherent framework. According to quantum field theory, particles are not fundamental objects but rather excitations and underlying fields that permeate all of space and time. In this view, particles such as electrons or photons are simply ripples or waves in their respective fields. These fields are everywhere, and the properties of particles are determined by how they interact with these fields. This theory introduces an entirely new way of thinking about reality. If particles are not solid objects but excitations in invisible fields, then what we perceive as physical matter is not as concrete as we once believed. The boundaries between particles, fields, and space itself become blurred. This could help explain phenomena like quantum entanglement, where particles seem to communicate instantaneously over vast distances, as the information might be transmitted through these underlying fields that span all of space. Quantum field theory also raises new questions about the nature of vacuum and empty space. In classical physics, a vacuum is simply the absence of matter, an empty void. But in quantum mechanics, even the vacuum is teeming with activity. The so-called quantum vacuum is a seething sea of virtual particles that constantly pop in and out of existence, borrowing energy from the vacuum itself before quickly annihilating each other. This strange phenomenon is known as quantum fluctuations, and it implies that what we think of as empty space is not empty at all but filled with a constant, invisible dance of particles and energy. These quantum fluctuations are not just theoretical curiosities. They have measurable effects on the universe. For example, the Casimir effect is a physical force that arises from quantum fluctuations between two closely spaced plates in a vacuum. This effect provides direct evidence that the quantum vacuum is not truly empty but filled with fluctuations that can influence physical objects. This also ties into the idea of zero-point energy, the lowest possible energy state of a quantum system, which suggests that even in its lowest energy state, space contains a non-zero amount of energy. The concept of quantum fluctuations has even led some physicists to propose that the entire universe might have arisen from nothing, through a process known as quantum tunneling. According to this idea, the universe could have emerged spontaneously from the quantum vacuum, without the need for a pre-existing cause. This mind-bending theory suggests that the universe itself is a kind of quantum fluctuation, a temporary bubble of spacetime that arose from the void and may one day collapse back into nothingness. This brings us to another deep mystery, the relationship between quantum mechanics and gravity. While quantum mechanics governs the behavior of particles at the smallest scales, gravity is the force that shapes the structure of the cosmos at the largest scales. However, despite the success of both quantum mechanics and general relativity, the two theories are fundamentally incompatible. This has led physicists to search for a theory of quantum gravity, a unified framework that can describe the behavior of gravity at the quantum level. One of the most promising candidates for a theory of quantum gravity is string theory. According to string theory, the fundamental building blocks of reality are not particles but tiny, vibrating strings of energy. These strings can vibrate at different frequencies, giving rise to the different particles we observe in the universe. In this view, all of the forces and particles in the universe, including gravity, are simply different vibrations of these fundamental strings. String theory also introduces the concept of extra dimensions, beyond the 3 dimensions of space and 1 dimension of time that we are familiar with. According to string theory, there may be additional hidden dimensions that are compactified, or curled up, at incredibly small scales, making them undetectable in everyday life. These extra dimensions could hold the key to understanding the fundamental nature of reality, as they might provide the missing link that unifies quantum mechanics and gravity. However, string theory is still highly speculative, and it has yet to be confirmed by experimental evidence. One of the biggest challenges is that the energy scales required to test string theory are far beyond what we can currently achieve in particle accelerators. Despite this, string theory has gained popularity among physicists because it offers a mathematically consistent framework for understanding quantum gravity and the fundamental nature of the universe. Another approach to quantum gravity is loop quantum gravity, which takes a different route by attempting to quantize space and time themselves. In loop quantum gravity, space is not a continuous, smooth fabric as described by general relativity, but rather consists of discrete, indivisible chunks called quantum loops. These loops form a kind of quantum lattice that gives rise to the structure of spacetime. According to this theory, at the smallest scales, space and time are not smooth and continuous but granular, like pixels in a digital image. Loop quantum gravity offers a radically different picture of the universe, where space and time themselves are emergent phenomena that arise from more fundamental quantum structures. This theory suggests that space and time may have a discrete, atomic structure, and that the fabric of spacetime could behave in strange and unexpected ways at the quantum level. For example, some versions of loop quantum gravity predict that time itself could become quantized, with time passing in discrete intervals rather than flowing smoothly. These competing theories of quantum gravity, string theory and loop quantum gravity, are at the forefront of modern physics, as scientists search for a unified theory that can explain both the quantum and cosmological realms. However, both theories face significant challenges, and neither has yet been confirmed by experimental evidence. The search for a theory of quantum gravity is one of the greatest unsolved mysteries in physics, and it may hold the key to unlocking the deepest secrets of the universe. As we continue to explore these mysteries, we are forced to confront questions that go beyond the realm of science and enter the domain of philosophy. What is the true nature of reality? Is the universe a deterministic machine, or is it governed by the strange and unpredictable laws of quantum mechanics? Does time flow in one direction, or is it an illusion created by our limited perception? And if the universe is indeed a quantum system, what role do we, as conscious observers, play in shaping the reality we experience? These questions delve into the very core of what it means to observe and experience reality. Quantum mechanics challenges the classical notion of an objective, observer-independent reality. One of the most controversial and puzzling aspects of quantum mechanics is the idea that the act of observation may influence the outcome of quantum events. This is encapsulated in what is known as the observer effect, which suggests that measuring a quantum system forces it to choose a definite state from the range of probabilities that describe it. The observer effect is most famously illustrated in the double-slit experiment. When particles, such as electrons, are fired at a barrier with 2 slits and are not observed, they behave like waves, creating an interference pattern on the screen behind the barrier. This wave-like behavior implies that the particles pass through both slits simultaneously, as if they exist in a superposition of states. However, when the particles are observed, they behave like particles, passing through one slit or the other, and the interference pattern disappears. This experiment highlights the strange duality between particles and waves in quantum mechanics, known as wave-particle duality. But more importantly, it raises the unsettling question: does reality only take a definite form when we observe it? Before we observe the particles, they seem to exist in a state of superposition, where all possible outcomes are equally real. Only when we make a measurement does the system collapse into one of these possible outcomes. The implications of this are profound and have sparked intense debate among physicists and philosophers alike. If reality depends on observation, then what is the role of the observer? Does consciousness itself play a fundamental role in shaping the universe? Some interpretations of quantum mechanics, such as the Copenhagen interpretation, suggest that the act of measurement is what causes the collapse of the wave function, bringing about a concrete reality from the nebulous realm of quantum probabilities. Yet, other interpretations challenge this view. The many worlds interpretation, for example, posits that there is no collapse of the wave function. Instead, all possible outcomes of a quantum event occur simultaneously, but in separate, branching universes. According to this theory, every time a quantum event happens, the universe splits into multiple parallel realities, each representing a different outcome. In one universe, the electron passes through the left slit, while in another, it passes through the right slit. This interpretation suggests that we live in a vast multiverse, where every possible outcome of every event is realized in some alternate reality. While this idea may seem speculative and far-fetched, it offers a way to preserve the determinism of quantum mechanics without invoking the mysterious role of the observer. However, it also implies that there are countless versions of ourselves living out different lives in different branches of the multiverse, a concept that raises profound philosophical questions. Another interpretation that addresses the observer effect is the pilot wave theory, also known as the Broglie theory. This theory proposes that particles always have definite positions and trajectories, guided by an underlying wave. In this view, the strange behavior of particles in quantum experiments is not due to the particles themselves being in superposition but rather the influence of the guiding wave, which interacts with the particles in a non-local manner. The pilot wave theory restores a sense of determinism to quantum mechanics, suggesting that particles follow well-defined paths, even if we cannot predict them precisely. The pilot wave theory, like many worlds, challenges the conventional Copenhagen interpretation and raises new questions about the nature of reality. If particles have definite positions and are guided by an invisible wave, then perhaps the randomness of quantum mechanics is not fundamental but merely a reflection of our ignorance about the true, underlying dynamics of the system. This leads to a broader question: are the apparent mysteries of quantum mechanics simply the result of our incomplete understanding, or do they reveal something fundamentally unknowable about the universe? Regardless of the interpretation one subscribes to, it is clear that quantum mechanics has forced us to rethink our understanding of reality. The classical worldview, which sees the universe as a clockwork mechanism governed by deterministic laws, has given way to a much stranger and more mysterious picture of the cosmos. In the quantum world, particles can exist in multiple places at once, influence each other across vast distances, and seem to change their behavior depending on whether they are being observed. But perhaps the most mind-bending implication of quantum mechanics is the possibility that reality itself is not as fixed or objective as we once believed. If quantum systems exist in a superposition of states until they are measured, then it may suggest that reality is not a pre-existing entity that we passively observe but something that is actively shaped by our interactions with it. This idea challenges the very foundations of classical physics, which assumes that the universe exists independently of our observations. Some physicists and philosophers have even suggested that consciousness might play a fundamental role in shaping reality. According to this view, reality only takes on definite properties when it is observed by a conscious being. This idea is closely related to the notion of participatory realism, which suggests that the act of observation is not merely a passive process but an active one that brings reality into existence. In this view, the universe is not a fixed, objective entity but a dynamic, participatory system in which observers play a crucial role. One of the most famous proponents of this idea was the physicist John Archibald Wheeler, who proposed the concept of the participatory universe. According to Wheeler, the universe is fundamentally interactive, with observers playing a key role in shaping its structure and behavior. Wheeler famously said. We are not merely observers. We are participators. In some strange sense, this is a participatory universe. This idea blurs the distinction between observer and observed, suggesting that the universe is not a static backdrop against which events unfold but a dynamic, evolving system that depends on the actions and observations of conscious beings. The participatory universe concept also raises questions about the nature of consciousness itself. If consciousness plays a fundamental role in shaping reality, then what is consciousness? Is it a purely emergent phenomenon, arising from the complex interactions of neurons in the brain, or is it something more fundamental, woven into the very fabric of the universe? Some physicists and philosophers have speculated that consciousness might be a fundamental aspect of reality, existing independently of physical matter. This idea is explored in the field of panpsychism, which suggests that consciousness is a universal feature of the cosmos, present in all matter to varying degrees. According to panpsychism, even elementary particles like electrons and quarks might possess a rudimentary form of consciousness, which becomes more complex as particles combine to form larger systems like molecules, cells, and eventually, human brains. While this idea is highly speculative and controversial, it offers a potential solution to the so-called hard problem of consciousness, the question of how subjective experience arises from physical processes. The hard problem of consciousness remains one of the greatest mysteries in both science and philosophy. Despite advances in neuroscience, we still do not understand how the brain generates the rich, subjective experience of consciousness. Some scientists argue that consciousness is simply an emergent property of complex information processing in the brain, while others believe that consciousness may require new, as yet undiscovered laws of physics to explain. One intriguing possibility is that quantum mechanics itself might play a role in consciousness. The physicist Roger Penrose and anesthesiologist Stuart Hameroff have proposed a theory known as orchestrated objective reduction, (OR), which suggests that quantum processes in the brain's microtubules, tiny structures within neurons, might be responsible for generating consciousness. According to this theory, consciousness arises when quantum superpositions in the microtubules collapse, creating a moment of conscious experience. While the orchestra theory remains speculative and controversial, it highlights the potential connections between quantum mechanics and consciousness. If quantum processes do play a role in consciousness, it could suggest that the mind is not merely a byproduct of physical matter but something deeply connected to the fundamental workings of the universe. If the orchestra theory or any similar quantum-based hypothesis about consciousness turns out to be true, it would revolutionize our understanding of both the mind and the universe. It would imply that the boundary between physical matter and subjective experience is far less rigid than we currently believe. This might suggest that consciousness and reality are interwoven at the deepest levels, possibly even implying that the universe itself possesses a kind of proto-consciousness, a notion aligned with some forms of panpsychism. These ideas have profound implications for the nature of reality itself. If consciousness is indeed tied to quantum mechanics, it could suggest that reality is not simply out there, in some objective sense, waiting for us to discover it. Instead, reality may be co-created by the interaction between the physical world and conscious observers. In this view, the universe is not a passive, static entity but a dynamic, participatory process in which the act of observation is fundamental to the emergence of a definite reality. This brings us back to the central mystery of quantum mechanics, the question of whether reality is observer-dependent. If the observer effect is real, and if the act of measurement indeed brings about a collapse of the wave function, then we may be forced to rethink our very understanding of what it means for something to exist. In classical physics, objects exist independently of whether they are being observed. But in quantum mechanics, existence seems to be more fluid, with particles and systems existing in a superposition of possible states until an observer collapses them into a definite reality. The philosophical implications of this are staggering. It challenges the long-held assumption that the universe exists in a fixed, objective state that we can explore and understand through observation. Instead, quantum mechanics seems to suggest that reality is deeply relational, that it only takes on specific properties when it interacts with a conscious observer. This raises profound questions about the nature of existence itself. Does the moon exist when no one is looking at it? Is reality real if no one is there to observe it? This conundrum is closely related to Schrödinger's cat thought experiment, a famous paradox that illustrates the strangeness of quantum mechanics. Schrödinger's cat imagines a scenario in which a cat is placed in a sealed box with a radioactive atom, a Geiger counter, and a vial of poison. The atom has a 50% chance of decaying within a certain period of time, which would trigger the Geiger counter, break the vial, and kill the cat. According to the Copenhagen interpretation of quantum mechanics, the cat is in a superposition of being both alive and dead until someone opens the box and observes it. This paradox highlights the bizarre implication that quantum systems can exist in multiple states simultaneously until they are observed. But Schrödinger's cat also raises a deeper question: is there an objective reality independent of observation? In the case of the cat, it seems absurd to suggest that it is both alive and dead at the same time. Yet, if quantum mechanics applies to all systems, including macroscopic ones like cats, then we are forced to accept that the cat exists in a superposition of states until the moment of observation. This suggests that reality itself may not be fixed but rather contingent on observation. Some interpretations of quantum mechanics, such as the many worlds interpretation, sidestep this problem by suggesting that the cat is both alive and dead, but in different parallel universes. In one universe, the atom decays, the Geiger counter triggers, and the cat dies. In another, the atom does not decay, and the cat remains alive. According to this view, every possible outcome of a quantum event is realized in some branch of the multiverse. This avoids the need for a collapse of the wave function but introduces the equally mind-bending idea that reality is constantly splitting into countless parallel worlds. If the many worlds interpretation is correct, then every quantum event results in the creation of new universes, each representing a different outcome. This leads to a dizzying picture of the cosmos, in which an infinite number of parallel realities exist, each slightly different from the others. In one universe, you might be reading this essay, while in another, you are doing something entirely different. The implications of this are vast, not only for physics but for philosophy, ethics, and our understanding of the self. For instance, the many worlds interpretation raises questions about personal identity and free will. If every possible version of yourself exists in some parallel universe, then what does it mean to be you? Are you just one of many copies, all equally real? And if every possible outcome of your decisions is realized in some universe, do you truly have free will, or are all your choices predetermined in the grand tapestry of the multiverse? The philosophical questions posed by quantum mechanics and the many worlds interpretation are not just abstract musings. They touch on fundamental aspects of human existence. What is reality? What is consciousness? What does it mean to make choices and to be aware of the world? These are questions that have fascinated philosophers for millennia, but quantum mechanics has brought them into the realm of science, forcing us to grapple with them in new and unexpected ways. In addition to the many worlds interpretation, other interpretations of quantum mechanics attempt to explain the mysteries of the observer effect and the nature of reality. One such interpretation is known as objective collapse theory, which suggests that wave function collapse is a real, physical process that happens spontaneously, without the need for an observer. According to this view, quantum superpositions are unstable and eventually collapse into a definite state after a certain amount of time, or when the system reaches a certain size or complexity. Objective collapse theories aim to provide a more intuitive explanation for why we don't observe quantum superpositions in the macroscopic world. After all, while particles like electrons and photons can exist in superpositions, we never see cats, chairs, or planets in multiple states at once. Objective collapse theory suggests that quantum mechanics only applies to small systems, and that larger systems collapse into definite states due to some as yet undiscovered physical mechanism. However, objective collapse theories come with their own challenges. If wave function collapse is a real, physical process, then it must be governed by some set of laws. But what are those laws, and why do they only apply to certain systems? Moreover, objective collapse theories imply that there is something fundamentally different about quantum systems compared to classical ones, which raises the question of where the boundary between the quantum and classical worlds lies. Another intriguing interpretation is quantum Bayesianism, or QBism, which takes a radically different approach to the nature of quantum mechanics. According to QBism, the wave function does not represent an objective physical reality, but rather an observer's subjective knowledge or beliefs about a system. In this view, quantum mechanics is not about the external world but about how observers update their knowledge based on measurements. QBism shifts the focus away from the nature of reality and onto the role of the observer, treating quantum mechanics as a tool for making predictions rather than a description of an underlying reality. This interpretation avoids many of the paradoxes of quantum mechanics by denying that the wave function corresponds to anything real, out there, in the world. Instead, it is a mathematical tool that helps observers make sense of their experiences. While QBism is a minority view among physicists, it offers an intriguing solution to some of the conceptual problems of quantum mechanics. By treating the wave function as a representation of knowledge rather than reality, it sidesteps the need to explain wave function collapse or superpositions in the macroscopic world. However, it also raises questions about the nature of reality itself. If the wave function is not real, then what is? And if quantum mechanics is just about making predictions, does it tell us anything fundamental about the universe? Each of these interpretations of quantum mechanics, Copenhagen, many worlds, pilot wave, objective collapse, QBism, offers a different perspective on the nature of reality. But none of them fully resolves the mysteries of the quantum world. Instead, they each highlight different aspects of the problem, raising new questions while offering partial answers. What all these interpretations share, however, is a recognition that reality is far stranger and more mysterious than we ever imagined. Quantum mechanics has revealed a world where particles can be in multiple places at once, where distant objects can instantaneously affect each other, and where the very act of observation can shape the outcome of events. It has forced us to confront the limits of our knowledge and to question the very nature of existence. But the mysteries of quantum mechanics are not confined to the microscopic realm. They also have profound implications for our understanding of the cosmos as a whole. Quantum mechanics plays a crucial role in cosmology, particularly in the study of the early universe and the fundamental forces that govern its evolution. The Big Bang, the expansion of the universe, the formation of galaxies, all of these phenomena are deeply connected to the principles of quantum mechanics. For example, one of the most important discoveries in modern cosmology is the concept of cosmic inflation, a rapid expansion of the universe that occurred in the first fractions of a second after the Big Bang. Inflation theory explains many of the observed features of the universe, such as its large-scale structure and the uniformity of the cosmic microwave background radiation. But inflation is also intimately connected to quantum mechanics. During the inflationary period, tiny quantum fluctuations in the fabric of spacetime were stretched to cosmic scales, seeding the formation of galaxies and other structures in the universe. These quantum fluctuations, which originated at the smallest possible scales, were amplified by inflation, leading to the large-scale structures we see today. In this way, quantum mechanics plays a fundamental role in shaping the universe, from the smallest particles to the largest galaxies. The connection between quantum mechanics and cosmology is also evident in the study of black holes. Black holes are some of the most mysterious objects in the universe, and their behavior challenges our understanding of both quantum mechanics and general relativity. In particular, the study of black hole thermodynamics and the information paradox has led to deep insights into the nature of quantum mechanics and the structure of spacetime itself. The information paradox arises from a conflict between quantum mechanics and general relativity, particularly in the context of black holes. According to classical general relativity, when something falls into a black hole, it is lost forever. The black hole's event horizon acts as a one-way barrier, and whatever crosses it is trapped inside, eventually reaching the singularity at the center, where the laws of physics as we know them break down. However, quantum mechanics suggests that information can never be truly lost. This principle, known as quantum unitarity, asserts that the evolution of quantum systems is reversible, meaning that all information about a system's past should, in theory, be recoverable. But when something falls into a black hole, it seems that the information about its initial state is lost forever. This apparent contradiction between the two theories, general relativity's prediction of information loss and quantum mechanics' insistence on its preservation, is what creates the information paradox. This paradox was brought to prominence by physicist Stephen Hawking, who showed that black holes are not entirely black but emit a faint form of radiation, now known as Hawking radiation. Over time, this radiation causes black holes to lose mass and eventually evaporate completely. The puzzle is, if a black hole can eventually disappear, what happens to the information about the objects that fell into it? If the black hole evaporates entirely, does the information simply vanish? If so, that would violate the core tenet of quantum mechanics. The information paradox has led to many theories and debates within the physics community. One possible solution comes from the concept of black hole complementarity, which suggests that information is somehow both reflected at the event horizon and absorbed by the black hole, depending on the perspective of the observer. However, this interpretation raises its own set of challenges, including the infamous firewall paradox, which suggests that an observer falling into a black hole would encounter a searing wall of radiation at the event horizon, contradicting the classical idea that crossing the horizon should be uneventful. Another possible resolution to the information paradox lies in the idea of holography, specifically the holographic principle. This principle, first proposed by physicists Gerard T. Hooft and Leonard Susskind, suggests that all the information contained within a volume of space can be encoded on its boundary, much like a hologram. In the case of a black hole, this would mean that the information about everything that falls into the black hole is somehow encoded on the event horizon. This idea led to the development of the anti-de Sitter/conformal field theory, ADS/CFT, correspondence, a groundbreaking concept in theoretical physics that posits a deep connection between gravity in higher dimensional space and quantum field theory on its lower dimensional boundary. The holographic principle has profound implications, not just for black holes but for our understanding of reality itself. It suggests that the three-dimensional universe we experience may, in fact, be a projection of information encoded on a distant, two-dimensional boundary. This mind-bending idea challenges our most basic assumptions about space, time, and the nature of existence. If the holographic principle is correct, it could offer a pathway to reconciling quantum mechanics and general relativity, two of the most successful yet seemingly incompatible theories in physics. The search for a theory of quantum gravity, a framework that unites the principles of quantum mechanics with the geometric description of spacetime provided by general relativity, has been one of the most important quests in modern physics. Various approaches, including string theory, loop quantum gravity, and others, have been proposed, but so far, no theory has achieved complete success. String theory, in particular, is one of the leading candidates for a theory of quantum gravity. It posits that the fundamental building blocks of the universe are not particles but tiny, vibrating strings of energy. These strings can vibrate at different frequencies, giving rise to the various particles we observe. String theory also requires the existence of additional spatial dimensions beyond the familiar 3, with some versions of the theory positing up to 11 dimensions. While string theory offers many intriguing possibilities, it remains highly speculative, and experimental evidence for it is currently lacking. Nevertheless, string theory has provided valuable insights into the nature of black holes, spacetime, and quantum gravity. One of its most important contributions is the discovery of dualities, mathematical relationships that reveal deep connections between seemingly different physical theories. For example, ADS/CFT duality suggests that certain gravitational systems in higher dimensions can be described by quantum field theories without gravity in lower dimensions. This duality provides a powerful tool for studying black holes, quantum gravity, and even the nature of the universe itself. The quest for quantum gravity has also led to the development of other intriguing ideas, such as loop quantum gravity (LQG). LQG proposes that spacetime itself is not continuous but consists of discrete, quantized units, much like how matter is made up of atoms. In this view, spacetime is a kind of fabric woven from tiny loops or spin networks. which are the fundamental building blocks of the universe. Loop quantum gravity offers an alternative to string theory, but it, too, remains a work in progress, with many questions yet to be answered. One of the most exciting frontiers in the study of quantum mechanics and the nature of reality is the ongoing research into quantum gravity and the nature of spacetime. At the Planck scale, the smallest possible scale, where quantum effects dominate, our classical notions of space and time break down. At this scale, spacetime becomes a seething, chaotic foam of quantum fluctuations, where particles pop in and out of existence, and the familiar fabric of reality unravels. Understanding the nature of spacetime at the Planck scale is one of the greatest challenges in physics. It is here that quantum mechanics and general relativity must be reconciled, and it is here that we may uncover the true nature of reality. Some physicists believe that spacetime itself may emerge from more fundamental, quantum-level processes, and that the fabric of the universe is not as solid or continuous as it appears. Instead, spacetime may be a kind of emergent phenomenon, arising from deeper, quantum-level interactions. These ideas are still in their infancy, but they hint at a future where quantum mechanics, general relativity, and the nature of reality itself are understood in a new, unified framework. As physicists continue to probe the mysteries of the universe, from the smallest particles to the largest cosmological structures, we may one day arrive at a deeper understanding of the cosmos and our place within it. But for now, the mysteries of quantum mechanics and the nature of reality remain tantalizingly out of reach. The more we learn about the quantum world, the more we are confronted with paradoxes and puzzles that challenge our most basic assumptions. What is reality? What is the role of the observer? How does the universe, at its most fundamental level, operate? These are questions that have puzzled scientists and philosophers for centuries, and while quantum mechanics has provided many answers, it has also opened the door to new and deeper mysteries. Quantum mechanics forces us to confront the limits of our knowledge and the complexity of the universe. It reveals a reality that is far more intricate, interconnected, and mysterious than we ever imagined. And as we continue to explore the quantum realm, we may find that the answers to our deepest questions about the nature of existence lie not in the stars, but in the smallest, most fundamental building blocks of the universe, the particles, waves, and fields that make up the quantum world. As we delve deeper into the realm of quantum mechanics, we must also consider the philosophical implications of these discoveries. The nature of reality, as revealed through quantum mechanics, challenges our intuitive notions of space, time, and causality. One of the most intriguing aspects of quantum mechanics is the role of the observer in determining the state of a system, a phenomenon that has led to numerous interpretations and debates among physicists and philosophers alike. The Copenhagen interpretation, primarily associated with Niels Bohr and Werner Heisenberg, posits that until a measurement is made, a quantum system exists in a superposition of states. This means that a particle can be in multiple states simultaneously, and it is only upon observation that the wave function collapses into a definite state. This interpretation suggests that reality is fundamentally probabilistic, and that our observations play a crucial role in shaping the universe. However, this raises profound questions. Does consciousness influence the outcome of quantum experiments? Is there an objective reality independent of observation, or is reality intrinsically linked to our perception of it? In contrast to the Copenhagen interpretation, the many worlds interpretation, introduced by Hugh Everett III, takes a radically different approach. According to this interpretation, every time a measurement is made, the universe splits into multiple branches, each representing a different outcome of the measurement. In this view, all possible outcomes coexist in a vast multiverse, where every possibility is realized in some branch of reality. While this interpretation resolves the issue of wave function collapse, it raises its own set of philosophical challenges. What does it mean to say that an infinite number of realities exist simultaneously? How does this affect our understanding of free will and decision-making? Another interpretation worth exploring is the de Broglie theory, also known as pilot wave theory. This interpretation introduces hidden variables that guide the behavior of quantum particles, suggesting that particles have definite positions and velocities at all times, even when not being observed. While this approach restores a sense of determinism to quantum mechanics, it still grapples with the implications of non-locality, how particles can instantaneously affect each other regardless of distance, as demonstrated by the phenomenon of entanglement. Entanglement is perhaps one of the most bizarre and fascinating aspects of quantum mechanics. When two particles become entangled, their properties become interconnected in such a way that the state of one particle cannot be described independently of the state of the other, no matter how far apart they are. This phenomenon has been experimentally verified and is at the heart of many quantum technologies, including quantum computing and quantum cryptography. Entanglement challenges our traditional notions of locality and causality, leading to the concept of spooky action at a distance, a phrase coined by Albert Einstein, who was famously skeptical of the implications of quantum mechanics. The idea that information or influence can travel instantaneously across vast distances defies our understanding of space and time as separable entities. Yet, numerous experiments have confirmed the reality of entanglement, forcing us to reconsider the fundamental structure of reality itself. As we explore these concepts, we encounter the philosophical implications of quantum mechanics that resonate far beyond the laboratory. The question of reality, as we perceive it, becomes increasingly complex. Are we simply observers in a vast multiverse, or do our choices and actions influence the fabric of reality itself? This intersection of physics and philosophy raises profound questions about the nature of existence, consciousness, and the universe. The concept of quantum mechanics also opens the door to discussions about technology and its impact on society. Quantum computing, which leverages the principles of superposition and entanglement, has the potential to revolutionize the way we process information. Unlike classical computers, which rely on bits that can represent either a 0 or a 1, quantum computers use qubits that can exist in multiple states simultaneously. This allows quantum computers to solve complex problems much more efficiently than classical computers, with potential applications ranging from cryptography to drug discovery. However, as we develop quantum technologies, we must also grapple with the ethical implications of their use. Quantum computing could disrupt industries, create new forms of cybersecurity threats, and challenge our understanding of privacy and information security. The dual-edged nature of these advancements forces us to consider how we navigate the intersection of science, technology, and ethics in a rapidly evolving landscape. Moreover, as we attempt to understand the quantum realm, we also face the challenge of reconciling quantum mechanics with our understanding of the universe on cosmic scales. Cosmology, the study of the universe's origin and evolution, is deeply intertwined with quantum mechanics. The early universe, described by the Big Bang theory, was a hot, dense state governed by quantum fluctuations. Understanding how these fluctuations led to the large-scale structure of the universe we observe today is a critical area of research. Quantum fluctuations in the early universe may have seeded the formation of galaxies, stars, and planets. The inflationary model of cosmology, which posits a rapid expansion of the universe shortly after the Big Bang, provides a framework for understanding how quantum effects can influence cosmic structure. This inflationary phase, driven by quantum field dynamics, could explain the uniformity of the cosmic microwave background radiation and the large-scale distribution of galaxies. As we explore the cosmic implications of quantum mechanics, we must also confront the mysteries of dark matter and dark energy, two of the most enigmatic components of the universe. Dark matter, which does not emit or interact with electromagnetic radiation, is believed to constitute a significant portion of the universe's mass, influencing the motion of galaxies and galaxy clusters. Dark energy, on the other hand, is thought to be responsible for the accelerated expansion of the universe. Both dark matter and dark energy present profound challenges for physicists and cosmologists, as their true nature remains elusive. In recent years, researchers have begun to explore potential connections between quantum mechanics and dark matter. Some theories suggest that dark matter could be composed of exotic particles that exhibit quantum behavior. Others propose that dark matter might be a manifestation of quantum entanglement or other quantum phenomena. The search for a deeper understanding of dark matter may ultimately require a synthesis of quantum mechanics and cosmology, leading to new insights into the fundamental workings of the universe. As we stand at the intersection of quantum mechanics, philosophy, and cosmology, we are reminded of the profound mysteries that still lie ahead. The universe, at its most fundamental level, remains an enigma, a tapestry woven from the threads of quantum phenomena, spacetime dynamics, and cosmic evolution. Our journey through this landscape invites us to explore not only the nature of reality, but also our place within it. As we continue to probe the depths of quantum mechanics and the cosmos, we may discover that the universe is far more interconnected and intricate than we ever imagined. The exploration of quantum mechanics is not merely an academic pursuit, it is a journey into the very nature of existence. Each new discovery, each new insight, brings us closer to understanding the complex web of relationships that bind us to the universe. In this quest for knowledge, we must also acknowledge the limits of our current understanding. Quantum mechanics challenges our intuition and forces us to confront the unknown. It invites us to ask questions that have no easy answers and to embrace the uncertainties that lie at the heart of existence. As we grapple with these mysteries, we are reminded of the beauty and complexity of the universe. A universe that continues to unfold before our eyes, revealing its secrets layer by layer. As we stand on the precipice of discovery, the interplay between quantum mechanics and the nature of reality beckons us to explore further. The journey ahead promises to be filled with wonder, revelation, and the potential for profound transformation in our understanding of the cosmos. In the words of the physicist Richard Feynman, "The more I learn about the universe, the more I realize I don't understand." It is this sense of curiosity and wonder that drives us to continue our exploration of the mysteries of the quantum realm, the nature of reality, and the vast, interconnected tapestry of the universe. The quest for understanding in quantum mechanics is often likened to navigating a labyrinth, where each turn can lead to new insights or confounding paradoxes. At its core, quantum mechanics dismantles the classical view of the universe as a deterministic system governed by clear laws and predictable outcomes. Instead, it reveals a realm where probabilities reign supreme, and the very act of observation can alter the outcome of events. One of the most famous thought experiments illustrating the peculiar nature of quantum mechanics is Schrödinger's cat. In this scenario, a cat is placed inside a sealed box along with a radioactive atom, a Geiger counter, and a vial of poison. If the atom decays, it triggers the Geiger counter, which breaks the vial and kills the cat. If the atom does not decay, the cat remains alive. According to quantum mechanics, until the box is opened and an observation is made, the cat is simultaneously alive and dead, existing in a superposition of states. This thought experiment encapsulates the strange interplay between observation and reality, prompting us to question the very fabric of existence. As we ponder Schrödinger's cat, we are led to consider the implications of quantum superposition and entanglement in our understanding of consciousness. Some researchers have posited that consciousness itself may play a role in collapsing the wave function, suggesting a connection between the observer and the observed that transcends mere measurement. This idea raises profound questions about the nature of consciousness and its relationship to the physical universe. Is consciousness a fundamental aspect of reality, or is it merely an emergent property of complex systems? As we seek answers to these questions, we may find ourselves venturing into the realms of philosophy, cognitive science, and even spirituality. The exploration of quantum consciousness has gained traction in recent years, with theories such as those proposed by physicist Roger Penrose and anesthesiologist Stuart Hameroff. Their orchestrated objective reduction, (OR) theory suggests that quantum processes occurring within neurons may give rise to consciousness. According to this view, quantum coherence plays a vital role in our experience of awareness, bridging the gap between the quantum and classical realms. While this theory remains controversial and lacks empirical validation, it exemplifies the exciting interplay between quantum mechanics and the study of consciousness. As we continue our journey into the quantum realm, we encounter the concept of quantum teleportation, a phenomenon that further blurs the lines between reality and perception. Quantum teleportation involves the transfer of quantum information from one particle to another without physically transmitting the particle itself. This process relies on the principles of entanglement and superposition, enabling the instantaneous transfer of information across distances. While this may sound like science fiction, it has been experimentally demonstrated with photons and atoms. Quantum teleportation challenges our understanding of communication and information transfer. If information can be transferred instantaneously across vast distances, what does this imply for our notions of space, time, and causality? The implications of quantum teleportation extend beyond theoretical exploration. They also hold promise for the development of quantum communication technologies, which could revolutionize secure information transfer. At the heart of these explorations lies the question of reality. What is real? As we grapple with the findings of quantum mechanics, we are faced with the realization that our understanding of reality is not static but rather a dynamic interplay of observations, interactions, and probabilities. The quantum realm invites us to rethink our definitions of existence, urging us to consider a universe that is inherently uncertain, interconnected, and alive with possibilities. As we turn our attention to the implications of quantum mechanics for our everyday lives, we must acknowledge the growing influence of quantum technologies. Quantum computing, quantum cryptography, and quantum sensing are reshaping industries and redefining the boundaries of what is possible. For instance, quantum computers have the potential to solve complex problems that would take classical computers millions of years to compute. They can model intricate systems in chemistry, optimize supply chains, and enhance machine learning algorithms, heralding a new era of technological advancement. The impact of quantum mechanics extends beyond technology. It also reshapes our philosophical landscape. The implications of quantum mechanics have inspired thinkers and artists alike, fostering a cultural dialogue that transcends disciplines. From literature to visual arts, the themes of uncertainty, interconnectedness, and the nature of reality have found expression in diverse forms. This artistic exploration reflects the profound impact of quantum mechanics on our collective consciousness, urging us to grapple with the mysteries of existence and the nature of perception. As we reflect on the interplay between quantum mechanics and the nature of reality, we are reminded that our understanding of the universe is an ever-evolving tapestry. Each new discovery unveils layers of complexity, inviting us to question our assumptions and embrace the unknown. The mysteries of quantum mechanics serve as a reminder of the limitations of human understanding and the beauty of inquiry. In the spirit of exploration, we must also confront the limitations of current scientific paradigms. While quantum mechanics has provided profound insights into the workings of the universe, it remains an incomplete framework. The quest for a unified theory that reconciles quantum mechanics with general relativity, Einstein's theory of gravity, continues to be a central challenge for physicists. The search for a theory of everything, one that encompasses the fundamental forces of nature and explains the behavior of all matter, represents a frontier of scientific inquiry. One potential avenue for unification lies in string theory, which posits that fundamental particles are not point-like objects, but rather tiny vibrating strings. This framework suggests that the universe has additional dimensions beyond the familiar three dimensions of space and one of time. String theory has garnered significant attention and has the potential to bridge the gap between quantum mechanics and gravity. However, it remains largely theoretical, as experimental validation has proven elusive. As we explore the depths of quantum mechanics and its implications for the nature of reality, we are compelled to embrace the mysteries that lie at the forefront of scientific inquiry. The interplay between the observer and the observed, the probabilistic nature of quantum phenomena, and the intricate web of connections that bind the universe together are themes that resonate with our innate curiosity. The journey through the quantum realm is not merely an exploration of scientific concepts, it is a reflection of our collective quest for understanding. The mysteries of the universe beckon us to question our place within it, to ponder the nature of consciousness, and to explore the profound interconnectedness of all things. As we stand on the brink of discovery, we are reminded that the universe is a vast, intricate tapestry woven from the threads of quantum phenomena, cosmic evolution, and the richness of human experience. The exploration of quantum mechanics and the nature of reality is an ongoing journey, one that invites us to question our assumptions, embrace uncertainty, and seek deeper understanding. As we continue to probe the mysteries of the quantum realm, we may find that the answers we seek are not just scientific but deeply philosophical, illuminating the intricate connections between the observer and the universe. The future of quantum exploration holds great promise, and as we navigate this uncharted territory, we remain steadfast in our pursuit of knowledge. Each new discovery enriches our understanding of the cosmos and our place within it. As we stand at this crossroads of science and philosophy, we are reminded that the mysteries of the universe are not obstacles to overcome but invitations to explore, learn, and grow. Ultimately, the interplay between quantum mechanics and the nature of reality challenges us to reconsider our relationship with the universe. The questions we ask, the observations we make, and the connections we forge shape our understanding of existence. In this grand tapestry of reality, we are not merely passive observers, we are active participants in the unfolding story of the cosmos. As we look to the future, we must embrace the unknown and remain open to new perspectives and ideas. The exploration of quantum mechanics is an invitation to delve deeper into the mysteries of existence, to celebrate the beauty of inquiry, and to honor the intricate web of relationships that bind us to the universe. Together, let us embark on this journey of discovery, navigating the mysteries of quantum mechanics and the nature of reality, and embracing the profound wonder that lies at the heart of the cosmos. As we venture deeper into the realms of quantum mechanics and the nature of reality, it's important to recognize the critical role that experiments play in shaping our understanding. Quantum experiments have revealed a plethora of phenomena that challenge our classical intuitions and provide valuable insights into the underlying fabric of the universe. One of the most significant experimental tests of quantum mechanics is the double-slit experiment, which elegantly illustrates the wave-particle duality of matter. In the double-slit experiment, particles such as electrons or photons are directed toward a barrier with two slits. When both slits are open, and no measurement is made to determine which slit the particle passes through, an interference pattern emerges on a detection screen, indicating that the particles behave like waves. However, if a measurement is made to determine the particle's path, the interference pattern disappears, and the particles behave as classical particles, producing two distinct bands on the screen. This perplexing outcome raises fundamental questions about the role of observation in shaping reality. What does it mean for a particle to exist in a state of superposition, simultaneously traveling through both slits, until an observation collapses that state into a definitive outcome? The implications of the double-slit experiment extend far beyond the realm of physics, inviting us to reconsider our understanding of consciousness, perception, and the nature of reality itself. As we grapple with these ideas, we encounter the concept of quantum decoherence, which provides a framework for understanding how classical behavior emerges from quantum systems. Decoherence occurs when a quantum system interacts with its environment, causing the loss of coherence between quantum states, and leading to the apparent collapse of the wave function. This process helps to explain why we observe classical behavior in macroscopic objects while still acknowledging the underlying quantum nature of reality. Decoherence has significant implications for our understanding of the transition from the quantum to the classical world. It suggests that the classical world we experience is not a separate realm but rather an emergent property of quantum interactions. This realization forces us to confront the limitations of our classical intuitions and to appreciate the intricate connections between quantum phenomena and our everyday experiences. Another critical aspect of quantum mechanics is the phenomenon of quantum entanglement, which has garnered considerable attention in both scientific and philosophical circles. Entanglement occurs when two or more particles become correlated in such a way that the state of one particle is intrinsically linked to the state of another, regardless of the distance separating them. When a measurement is made on one entangled particle, the state of the other particle is instantaneously determined, even if it is light years away. This phenomenon raises profound questions about the nature of space, time, and causality. Einstein famously referred to quantum entanglement as spooky action at a distance, expressing skepticism about its implications. The phenomenon challenges our conventional notions of locality, the idea that objects are only directly influenced by their immediate surroundings. Entanglement suggests that the universe is interconnected in ways that transcend our classical intuitions, prompting us to consider the possibility of a non-local reality where particles can instantaneously influence one another across vast distances. The implications of quantum entanglement extend beyond philosophical musings. They have practical applications in the emerging field of quantum information science. Quantum entanglement serves as the foundation for quantum communication protocols, such as quantum key distribution, QKD, which enables secure information transfer between distant parties. By harnessing the power of entanglement, researchers are developing technologies that could revolutionize cybersecurity and information transmission. As we reflect on the interplay between quantum mechanics and the nature of reality, we are drawn to the question of determinism. Classical physics operates under the assumption that the universe is governed by deterministic laws, where the present state of a system can be used to predict its future state with precision. In contrast, quantum mechanics introduces an inherent element of randomness and uncertainty, suggesting that certain aspects of reality are fundamentally indeterminate. The probabilistic nature of quantum mechanics has sparked debates among physicists, philosophers, and theologians alike. Some argue that the inherent randomness of quantum events undermines the notion of free will, while others contend that it opens up new avenues for understanding human agency and decision-making. As we navigate these complex philosophical waters, we must grapple with the implications of quantum indeterminacy for our understanding of morality, choice, and the human experience. One intriguing perspective on this topic is the many-worlds interpretation of quantum mechanics, proposed by physicist Hugh Everett III in the 1950s. According to this interpretation, every quantum event creates a branching of the universe into multiple, non-communicating parallel realities. In this view, all possible outcomes of a quantum event coexist simultaneously in their respective branches, leading to a vast multiverse of possibilities. The many-worlds interpretation challenges our traditional notions of causality and individuality, suggesting that each choice we make may give rise to a new, distinct reality. While the many-worlds interpretation offers a compelling framework for understanding quantum phenomena, it also raises profound philosophical questions. If all possible outcomes exist in parallel realities, what does that imply for our sense of self and the continuity of our experiences? Are we merely passengers in a vast multiverse, or do our choices and actions hold significance in shaping our personal narratives? As we ponder these questions, we must also consider the implications of quantum mechanics for our understanding of time. The nature of time has long been a subject of fascination for scientists and philosophers alike, and quantum mechanics adds yet another layer of complexity to this enigmatic concept. In classical physics, time is viewed as a linear progression, with past, present, and future existing as distinct and separate entities. However, in the quantum realm, time appears to behave differently, leading some researchers to propose alternative models of temporal existence. One such model is the block universe theory, which posits that past, present, and future events coexist in a timeless block. According to this perspective, the flow of time is an illusion, and all moments are equally real. This view aligns with certain interpretations of quantum mechanics, where time may emerge from the underlying quantum processes rather than being a fundamental aspect of reality. The block universe theory challenges our intuitive understanding of time and invites us to reconsider our perceptions of change, causality, and the nature of existence. As we navigate the complexities of quantum mechanics and the nature of reality, we are confronted with a tapestry of interconnected ideas and concepts. The interplay between observation and reality, the role of consciousness, the implications of entanglement, and the nature of time all invite us to delve deeper into the mysteries of existence. Each discovery, each experiment, and each theoretical exploration adds a new thread to the rich fabric of our understanding. The exploration of quantum mechanics is not merely an academic endeavor. It is a journey of discovery that transcends disciplines and invites us to reflect on our place in the universe. The mysteries of the quantum realm challenge our assumptions, provoke our imaginations, and inspire our curiosity. As we stand on the precipice of discovery, we are reminded that the quest for understanding is an ever-evolving process, one that encourages us to embrace uncertainty, question our beliefs, and remain open to the wonders of existence. As we look to the future, the potential of quantum mechanics continues to unfold. The fusion of science and philosophy, the exploration of consciousness, and the development of quantum technologies promise to shape our understanding of reality in ways we cannot yet fathom. Each new revelation adds depth to the intricate tapestry of existence, inviting us to embark on a lifelong journey of inquiry and wonder. In this grand adventure, we are not alone. We are part of a vibrant community of thinkers, dreamers, and explorers who seek to unravel the mysteries of the cosmos. Together, we embrace the unknown, celebrate the beauty of discovery, and honor the interconnectedness of all things. The universe, in all its complexity and majesty, invites us to question, explore, and celebrate the mysteries of life and existence. The story of quantum mechanics and the nature of reality is far from complete. As we continue to probe the depths of the quantum realm, we open ourselves to new insights and perspectives that may forever alter our understanding of the universe. In this ongoing exploration, let us remain curious, engaged, and inspired by the wonders that await us in the vast expanse of existence. As we delve deeper into the intricate landscape of quantum mechanics and its implications for our understanding of reality, we must also consider the role of experiments that continue to challenge our perceptions of what is possible. One of the most fascinating areas of study in contemporary physics is the phenomenon of quantum teleportation. This process involves the transfer of quantum information from one particle to another, seemingly instantaneously, without the physical movement of the particles themselves. While this might sound like science fiction, it is a real phenomenon that has been experimentally demonstrated. Quantum teleportation relies on the principles of quantum entanglement. When two particles are entangled, a measurement made on one particle affects the state of the other, regardless of the distance between them. In a teleportation experiment, the state of a particle is destroyed at its original location, while an identical copy of that state is created at a distant location through the use of entangled particles and classical communication. Although no physical object is transmitted, the information about the particle state is effectively teleported. The implications of quantum teleportation are profound, suggesting new possibilities for secure communication and information processing. In the realm of quantum computing, teleportation could enable the transfer of quantum states between qubits, which are the building blocks of quantum computers. This advancement could pave the way for more powerful and efficient computational systems that harness the unique properties of quantum mechanics. Yet, as we explore these frontiers, we must grapple with the philosophical implications of such phenomena. The idea that information can be transmitted instantaneously raises questions about the nature of information itself. Is information a fundamental aspect of reality, akin to matter and energy, or is it merely a construct of human understanding? Moreover, what does it mean for the concept of identity if the original state of a particle is destroyed during teleportation? These questions challenge our intuitions about continuity and the essence of existence. In addition to teleportation, researchers are investigating the phenomenon of quantum superposition, which allows particles to exist in multiple states simultaneously until measured. Superposition is at the heart of quantum computing, where qubits can represent both 0 and 1 at the same time, vastly increasing the potential computational power compared to classical bits. However, this principle also raises intriguing questions about the nature of reality. If a qubit can exist in a superposition of states, what does that imply for our understanding of determinism and the unfolding of events in the universe? One approach to understanding superposition is through the lens of the Copenhagen interpretation, which posits that a quantum system exists in a state of superposition until observed, at which point it collapses into a definite state. However, alternative interpretations, such as the many-worlds interpretation discussed earlier, suggest that all possible outcomes coexist in parallel realities. This divergence in interpretations highlights the challenges of reconciling quantum mechanics with our intuitive understanding of reality. To further explore the intersection of quantum mechanics and reality, we turn our attention to the concept of consciousness. The relationship between quantum mechanics and consciousness has sparked debate and speculation among scientists and philosophers. Some theorists propose that consciousness itself may play a role in the collapse of the wave function, suggesting that observation is not merely a passive act but an active participant in shaping reality. This idea invites us to consider the nature of consciousness as a fundamental aspect of existence, intricately linked to the fabric of the universe. One prominent figure in this discussion is physicist Eugene Wigner, who argued that consciousness is essential for the completion of quantum mechanics. He suggested that the act of observation, performed by a conscious observer, is what brings the probabilistic nature of quantum mechanics into the realm of definite outcomes. This perspective raises questions about the implications of consciousness for our understanding of reality, suggesting that the act of knowing may shape the universe in ways we have yet to comprehend. Despite its intriguing potential, the idea that consciousness influences quantum processes is controversial and remains an area of active research. Some scientists advocate for a more materialistic view, emphasizing that consciousness emerges from complex biological processes rather than being a fundamental feature of reality. This debate reflects the broader philosophical inquiry into the nature of existence, consciousness, and the interplay between the observer and the observed. As we navigate these complex questions, we encounter the notion of the observer effect, a fundamental principle in quantum mechanics that highlights the interplay between measurement and the state of a quantum system. The observer effect suggests that the act of measuring a quantum system influences its behavior, leading to the collapse of superpositions into specific outcomes. This phenomenon challenges our classical intuitions about objectivity and the separation of the observer from the observed. The observer effect has profound implications for our understanding of reality, suggesting that the universe is not a passive backdrop but an active participant in the act of observation. This realization invites us to reconsider the nature of reality itself. Are we mere spectators of a predetermined universe, or do our observations play a crucial role in shaping the unfolding of events? In exploring these ideas, we must also consider the implications of quantum mechanics for our understanding of time and causality. Traditional notions of cause and effect are challenged by the nonlinear and probabilistic nature of quantum events. The interconnectedness of quantum states suggests that the boundaries between past, present, and future may not be as clear-cut as we once believed. Some researchers propose that time itself may be an emergent property, arising from the underlying quantum processes that govern the universe. As we delve into the nature of reality, we are led to contemplate the question of existence itself. What does it mean to exist in a quantum universe where particles can be in multiple states simultaneously, and where entanglement creates a web of interconnectedness across vast distances? The exploration of these questions is not merely an academic exercise, it is a profound inquiry into the essence of being and the nature of the cosmos. Ultimately, the study of quantum mechanics invites us to embrace uncertainty and wonder. It challenges us to expand our horizons and rethink our understanding of existence. As we unravel the mysteries of the quantum realm, we find ourselves confronted with more questions than answers. Each revelation opens new avenues for exploration, compelling us to engage in an ongoing dialogue about the nature of reality. As we stand at the intersection of science and philosophy, we are reminded of the importance of curiosity and open-mindedness. The quest for understanding is a journey that transcends disciplines and invites us to explore the uncharted territories of existence. In this adventure, we are not merely passive observers, we are active participants in the unfolding story of the universe. The mysteries of quantum mechanics and the nature of reality are far from resolved. As researchers continue to probe the depths of the quantum realm, we can expect new discoveries that challenge our assumptions and expand our understanding. The interplay between quantum phenomena and our perceptions of reality serves as a reminder that the universe is a dynamic and ever-evolving tapestry, rich with complexity and wonder. The exploration of quantum mechanics is a journey that intertwines science, philosophy, and human experience. It challenges our intuitions, provokes our imaginations, and inspires our curiosity. As we continue to investigate the mysteries of the quantum realm, we are reminded that the quest for understanding is an ever-evolving process. We embrace the unknown, celebrate the beauty of discovery, and honor the interconnectedness of all things. The universe, in all its complexity, invites us to question, explore, and celebrate the wonders of existence. As we look toward the future, the potential of quantum mechanics remains boundless. The fusion of science and philosophy, the exploration of consciousness, and the development of quantum technologies promise to reshape our understanding of reality in ways we cannot yet comprehend. Each new revelation adds depth to the intricate tapestry of existence, inviting us to embark on a lifelong journey of inquiry and wonder. The story of quantum mechanics and the nature of reality is far from complete. As we continue to probe the depths of the quantum realm, we open ourselves to new insights and perspectives that may forever alter our understanding of the universe. In this ongoing exploration, let us remain curious, engaged, and inspired by the wonders that await us in the vast expanse of existence. As we continue to explore the profound implications of quantum mechanics and its relationship with the nature of reality, it becomes essential to consider the foundational theories that underpin our understanding of the quantum world. Central to this discussion is the notion of quantum fields, which extends our comprehension beyond individual particles to the underlying fields that permeate the universe. Quantum field theory posits that particles are excitations or disturbances in these fields, fundamentally altering our view of matter and energy. This field-based perspective leads to a deeper understanding of interactions at the quantum level. For instance, the electromagnetic field is responsible for the interactions between charged particles, such as electrons and protons. When we view particles as excitations in a field, we can better understand phenomena like particle creation and annihilation, where particles can emerge from and vanish into the vacuum of space. This realization challenges our traditional notions of conservation and prompts us to reevaluate the very fabric of reality. Furthermore, the principles of quantum mechanics suggest that the universe operates under a set of probabilistic laws rather than deterministic ones. This uncertainty is encapsulated in Heisenberg's uncertainty principle, which states that we cannot simultaneously know both the position and momentum of a particle with absolute precision. This inherent uncertainty raises philosophical questions about determinism and free will. If the universe operates on probabilities, to what extent can we claim to have control over our actions and decisions? The interplay of quantum uncertainty with our perception of free will continues to be a rich area for philosophical exploration. As we dive deeper into quantum mechanics, we encounter the concept of wave-particle duality. This phenomenon highlights that particles, such as electrons, can exhibit both wave-like and particle-like behavior depending on how they are observed. In the famous double-slit experiment, particles are fired at a barrier with two slits, creating an interference pattern that indicates wave-like behavior when not observed. However, when measurements are made to determine which slit a particle passes through, the interference pattern disappears, revealing particle-like behavior. This duality underscores the complexity of reality, suggesting that the act of observation is intimately linked to the fundamental nature of the universe. The implications of wave-particle duality extend beyond mere experimental observations. They challenge our understanding of reality itself. If particles can behave as both waves and particles, what does that imply for the nature of existence? This question leads us to ponder whether reality is a fixed structure or a fluid tapestry of possibilities, influenced by our observations and interactions. The philosophical ramifications of these ideas are profound, inviting us to reconsider the relationship between the observer and the observed. Moreover, the intersection of quantum mechanics with cosmology provides further avenues for exploration. The universe's earliest moments, right after the Big Bang, were characterized by extreme conditions that made classical physics inadequate for understanding the phenomena at play. Quantum fluctuations during this period may have seeded the large-scale structure of the universe, leading to the galaxies, stars, and planets we observe today. This connection between quantum mechanics and the origins of the cosmos invites us to reflect on our place in the universe and the fundamental processes that shape our reality. As we probe the mysteries of quantum mechanics, we encounter a rich tapestry of ideas that intertwine science, philosophy, and spirituality. The work of physicists such as David Bohm, who proposed a holistic interpretation of quantum theory, invites us to view the universe as an interconnected whole, where every particle is linked in a complex web of relationships. Bohm's notion of the implicate order suggests that the apparent separateness of objects is an illusion, and that reality is a unified whole that is constantly unfolding. In this framework, consciousness may play a pivotal role in the manifestation of reality. If our perceptions and observations influence the quantum realm, as suggested by the observer effect, then the relationship between consciousness and the universe becomes a critical area of inquiry. This line of thought resonates with various spiritual traditions that emphasize the interconnectedness of all things and the role of consciousness in shaping our experiences. The idea that consciousness could influence the fabric of reality also leads to intriguing discussions about the nature of human existence. If our thoughts and intentions can affect quantum processes, as some proponents of consciousness-based theory suggest, then we are not merely passive observers of reality but active participants in its creation. This perspective encourages us to explore the potential of consciousness as a creative force, prompting questions about how our beliefs and perceptions shape our experiences and the world around us. As we delve further into the relationship between quantum mechanics and consciousness, we encounter the concept of quantum biology. This emerging field studies how quantum effects may play a role in biological processes, such as photosynthesis and avian navigation. For instance, some studies suggest that the efficiency of energy transfer in photosynthesis may involve quantum coherence, allowing plants to utilize sunlight with remarkable efficiency. If quantum processes are indeed integral to biological functions, this connection could redefine our understanding of life itself and its relationship to the universe. The implications of quantum biology extend to the very nature of consciousness and awareness. If biological systems harness quantum effects, it raises questions about the origins of consciousness and its potential connections to the fundamental workings of the universe. This intersection of quantum mechanics and biology invites us to explore the deeper questions of what it means to be alive and aware in a universe governed by quantum laws. In contemplating the mysteries of quantum mechanics, we must also consider the role of technology in shaping our understanding of reality. The development of quantum technologies, such as quantum computing and quantum cryptography, is revolutionizing industries and pushing the boundaries of what is possible. Quantum computers leverage the principles of superposition and entanglement to perform complex calculations at unprecedented speeds, opening new frontiers in fields ranging from cryptography to drug discovery. However, with these advancements come ethical considerations. The power of quantum technologies raises questions about security, privacy, and the potential misuse of quantum capabilities. As we navigate this brave new world, it is imperative that we engage in thoughtful discourse about the implications of our technological progress and ensure that these advancements serve the greater good of humanity. As we explore the vast and intricate landscape of quantum mechanics and its implications for reality, we are reminded of the importance of curiosity, humility, and wonder. The universe is a complex and dynamic tapestry, rich with mysteries that continue to inspire our exploration and inquiry. Each revelation invites us to delve deeper, embrace uncertainty, and remain open to new ideas and perspectives. Ultimately, the journey through the quantum realm is a journey of discovery, not only of the universe around us but also of ourselves and our place within the cosmos. The interplay of science, philosophy, and spirituality challenges us to rethink our understanding of reality and embrace the interconnectedness of all things. As we stand on the precipice of new knowledge, we are called to be explorers, seekers of truth, and stewards of the wisdom that emerges from our exploration. The mysteries of quantum mechanics and the nature of reality beckon us to venture into the unknown. As we unravel the threads of existence, we are continually reminded of the beauty, complexity, and wonder of the universe. The interplay of quantum phenomena invites us to engage with profound questions about consciousness, existence, and the very fabric of reality itself. Each step we take in this exploration brings us closer to a deeper understanding of the cosmos and our place within it. As we look ahead, the journey through the quantum landscape promises to be filled with surprises, challenges, and revelations. The quest for knowledge is a shared endeavor, uniting scientists, philosophers, and curious minds across disciplines. Together, we embark on an adventure that transcends boundaries and invites us to ponder the mysteries of existence. In the tapestry of the universe, we are all interconnected threads, weaving a story of inquiry, wonder, and discovery that continues to unfold. Continuing from where we left off, the exploration of quantum mechanics and its relationship with reality opens up further avenues of inquiry that delve into the metaphysical implications of our findings. As we embrace the complexities of quantum phenomena, we encounter the challenge of reconciling our intuitive understanding of the world with the counterintuitive nature of quantum mechanics. This reconciliation is not merely an academic exercise. It shapes how we perceive ourselves and our place in the universe. One of the most captivating aspects of quantum mechanics is its impact on our understanding of time and space. Traditionally, we conceive of time as a linear progression from the past through the present and into the future. However, the principles of quantum mechanics suggest that time may not be as straightforward as we believe. In some interpretations, such as the block universe theory, all moments in time, past, present, and future, exist simultaneously. This notion challenges our conventional understanding of temporal flow and raises profound questions about causality and the nature of change. This concept also intersects with the theories of relativity proposed by Albert Einstein. In his theory of general relativity, space and time are intertwined in a four-dimensional continuum, suggesting that the fabric of the universe is dynamic and affected by mass and energy. As we explore the quantum realm, the fusion of quantum mechanics and relativity could pave the way for a more unified understanding of the universe. The quest for a theory of quantum gravity, a theoretical framework that reconciles the principles of quantum mechanics with those of general relativity, remains one of the most significant challenges in modern physics. To address these challenges, physicists have proposed various models, such as string theory and loop quantum gravity, each attempting to explain the fundamental workings of the universe. String theory posits that fundamental particles are not point-like objects but rather one-dimensional, strings, vibrating at different frequencies. This elegant framework offers the potential to unify all fundamental forces of nature, including gravity, into a single theoretical construct. However, string theory remains largely theoretical, with many of its predictions yet to be tested experimentally. As we contemplate the nature of reality through the lens of quantum mechanics and its implications for time and space, we are drawn into the realm of consciousness. The question of how consciousness arises from the quantum realm remains an open and contentious debate. Some theorists propose that consciousness is a fundamental aspect of the universe, akin to space and time. In this view, consciousness may play an active role in shaping reality rather than merely being a byproduct of complex biological processes. The implications of such a perspective are far-reaching. If consciousness is fundamental to the universe, it challenges us to reconsider our understanding of life and the nature of existence itself. It invites a more holistic view of the universe, where awareness and the fabric of reality are intertwined. This intertwining encourages a deeper inquiry into the nature of perception and the role of human experience in shaping our understanding of the cosmos. As we navigate this intricate landscape, we encounter the idea of the observer effect, which suggests that the act of observation influences the behavior of quantum systems. This phenomenon raises questions about the nature of reality when unobserved. Is there an objective reality that exists independently of observation, or does reality manifest through our conscious experiences? This question not only has profound implications for physics but also invites philosophical reflections on the nature of existence. Moreover, as we explore these concepts, we are compelled to consider the ethical implications of our understanding of consciousness and reality. The advancements in quantum technology, particularly in fields such as artificial intelligence and neuroscience, prompt us to reflect on the moral responsibilities that accompany our growing knowledge. As we develop technologies that can manipulate quantum systems and potentially influence consciousness, we must grapple with the ethical considerations of how these technologies are employed. The intersection of quantum mechanics and ethics invites us to explore the implications of our actions and decisions in a world governed by probabilistic laws. If our thoughts and intentions can influence reality, we bear a responsibility to cultivate awareness and mindfulness in our interactions with the world. This perspective encourages us to recognize the interconnectedness of all beings and the impact of our choices on the broader tapestry of existence. As we delve deeper into the mysteries of quantum mechanics, we must also acknowledge the limits of our current understanding. The complexity of the quantum realm often defies intuition, and many aspects remain elusive to our comprehension. This recognition of our limitations should not discourage us. Rather, it should inspire us to embrace curiosity and foster a spirit of inquiry. Throughout history, the pursuit of knowledge has been driven by a desire to understand the unknown. The mysteries of quantum mechanics are no exception. Each revelation, each experiment, brings us one step closer to a deeper understanding of the universe. As we grapple with the implications of our discoveries, we are reminded of the importance of interdisciplinary collaboration. The challenges posed by quantum mechanics extend beyond the boundaries of physics, inviting contributions from philosophy, biology, and even art. The role of art in interpreting the mysteries of quantum mechanics cannot be understated. Artists have long been at the forefront of exploring abstract concepts and conveying complex ideas through visual representation. The interplay of light and shadow, the dance of particles, and the interconnectedness of all things can be expressed through various artistic mediums. Art serves as a bridge between the scientific and the intuitive, allowing us to explore the emotional and experiential dimensions of our understanding of reality. As we contemplate the mysteries of the quantum realm, we must also consider the broader implications of our discoveries for humanity. The exploration of quantum mechanics is not merely an intellectual pursuit. It holds the potential to transform our relationship with the universe and ourselves. By embracing the uncertainties and complexities of the quantum world, we can cultivate a more profound sense of connection to the cosmos and to one another. In conclusion, the journey through quantum mechanics and the nature of reality invites us to confront our deepest assumptions and beliefs about existence. The interplay of consciousness, time, and the fundamental workings of the universe challenges us to explore the boundaries of knowledge and embrace the unknown. As we navigate the intricacies of quantum phenomena, we are reminded of the beauty and wonder that permeate the cosmos. Ultimately, the mysteries of quantum mechanics beckon us to engage with the profound questions of existence, consciousness, and the interconnectedness of all things. The pursuit of knowledge is a shared journey, uniting individuals across disciplines and inviting us to explore the tapestry of reality with curiosity, humility, and wonder. As we stand at the threshold of new discoveries, we are reminded that the quest for understanding is a never-ending adventure, one that continues to inspire generations of seekers, thinkers, and dreamers. In the grand tapestry of existence, we are all threads woven together, participating in the unfolding narrative of the universe. The mysteries of quantum mechanics serve as a reminder of the richness and complexity of our shared reality, urging us to remain open to the wonders that lie beyond our current understanding. As we embrace the unknown, we embark on a journey of exploration that transcends the boundaries of science, philosophy, and art, an adventure that invites us to ponder the very nature of reality itself. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.